Hi everybody. We're going to look today at logarithmic and exponential functions and their derivatives. You're going to see, I like using these functions a lot. The derivatives of them are actually very straightforward. So you're going to see some examples of using them. There'll be kind of three examples. We'll start with log, then we'll talk about the natural logarithm or the ln function, and then we'll talk about exponential functions or e. Okay, you've probably seen those all on your calculator. Starting at the beginning, remember that a logarithm, okay, is the number that comes out when you use the log button on your calculator is the exponent to which a certain base or number must be raised to produce that number, okay? So in other words, if you have a function y equals a to the exponent x, okay, what that means is if you take the log of it, you're taking the log, the base of that is a, in other words, the base of this exponent function, and the number you're using for the log, okay, is actually the number that's being output. So if you had 10 squared, 10 squared is equal to 100. How that would be set up is you would have the log, your base here is 10, and your number is 100. Okay, so if you go to your calculator and you type log 100, the answer you'll get is 2, okay, which matches that exponent. All right. Now, one thing that's important to note is your calculator assumes it's always base 10. Okay, so you might see questions that have log base 4 of a number, let's say 16. In that case, it'd be 2 because 4 squared is 16. But anytime you're using your calculator, unless you get into more expensive ones, the only one that they do is the base of 10. So that log button, you'll often just see it written as log, let's say log of 100, okay, with no base provided. And if that is the case, you have to assume that the base is 10, okay? In every instance, that means the base will be 10, okay? So knowing that, that's just basics of how logarithms work, okay? The derivative of a log function is pretty simple. So if you have the log, okay, of some function u, and it's at the base of a, then your derivative is 1 divided by u, or in other words, 1 divided by the function in here, times the log of e. Remember, e, known as Euler's number, is an irrational number. Okay, it's similar to the number pi in that it never, the decimal will never end. Okay, so it's not a defined number. So it's the log of that number e to this base a times the derivative of that u function, du by dx, or the easier way that I like to do it is to use the natural logarithm. Okay, so the natural logarithm involves the ln button. So if you look, this is a picture of my calculator, and most calculators are similar. You'll see, okay, that there's a log button, and right beside it is the ln button. Okay, so most of you will be familiar with this. But what makes it easier is, like I said, what's really hard is if the base here, okay, I'll change colors to purple. If the base here is not 10, if that value of a is something else, you can't put that in your calculator and obtain a number. So what you can do instead is, instead of having, I'm going to erase these arrows so you can see it a little better. Instead of having this log function, alternatively, the derivative is also equal to this. So it's the same thing, 1 divided by u, but it's multiplied by 1 divided by ln of that base, okay? So going back to, let's say you have this one here, log of 100, and the base is 10. That would make this ln of 10, okay? And the benefit of it is when you have ln, you can simply place that number directly in your calculator here, okay? Because we have a ln function, right? We're going to talk about natural logarithm and what it means after we do some logarithmic examples, but I'm showing you both ways to do the derivative. Either one you could do on a test and the answer is correct, but I'm going to strongly recommend that you use the one with the natural logarithm. Okay, so that's the one, it's not actually shown this way in your textbook, but I find it far easier when taking the derivative. Okay, so let's look at a few examples. Okay, so our first example, I'm going to do it showing both methods of the derivative. The first one that had the log function, and the second one that had ln. Okay, so you see two answers that I have written in the bottom corner here. I just want to kind of show you the differences between them. Okay, so find the derivative of y equals 4 log of x to the 5th plus 4. The first item to notice here is there's no base. Okay, so when there's no base, again, you assume that the base is 10. Okay, that's just a way that log has historically been written. So let's find the derivative first. Okay, method 1, we'll use the log version. Okay, so dy by dx is equal to 1 divided by u times the log, in this case to the base 10 of e, times du by dx. Okay, so u is whatever's in the brackets with log, so u is equal to x to the 5th plus 4, and du by dx would be equal to 5x to the 5 minus 1, okay? The derivative of number 4 is 0, so that's simply 5x to the 4th. So we have everything here to simply solve this, okay? So dy by dx is equal to, okay? In this instance, what I forgot to note here is you also have that number 4. So it's simply 4 times 1 divided by u, or 1 divided by x to the 5 plus 4, log base 10 of e, times du by dx, which is 5x to the 4th. Okay, so simplifying this, all right, we have 4 times 5x to the 4. The dy by dx is equal to 4 times 5x to the 4th is 20x to the 4th times the log of base 10 e, and then that's all divided by x to the 5th plus 4. Okay, so I just collected all the like terms in the numerator. All right, so that is using the derivative based on log. Okay, if we do this the second way, dy by dx is equal to, remember we have a constant 4, so we'll do 4 times 1 divided by u times 1 divided by the ln of the base. Okay, so in this case the base is 10, so ln 10, times du by dx. Okay, so everything is the same here, right? Our u value and our du by dx, nothing changes. The only piece, remember from that slide, that changed, sorry, that's not the color I wanted to use, so I'll use blue, is instead of log, we had ln. Okay, in this case, it's base 10, so both can be placed in your calculator, but if you do have it where it's not base 10, this is where it's really beneficial. So now I'm just going to substitute the values for u and du by dx. So dy by dx is equal to 4 times 1 divided by u, x to the 5th plus 4, times 1 divided by the ln of 10. Again, 10 is the base, okay, so it's always the ln of the base number, times du by dx, which is simply 5x to the 4. Okay, so again, I'm combining. In this case, I'll do, first step, I'll combine all the items in the numerator. So dy by dx is equal to, okay, we have 4 times 1 is 4, times 1 is 4, times 5x to the 4th, so that's 20x to the 4th. And then it's divided by, you can combine the two items together in the denominator. So you have ln of 10, and you multiply that by x to the 5th plus 4, the other item in the denominator. Okay, so you can see that the answers are very similar. The difference is you have the log function in the numerator here, and the ln function in the denominator here. Okay, again, either way you do this question is considered correct. I do want you to realize that when you start doing practice exercises, especially if you're trying to get to a final number, you'll notice that ln is far simpler to use. So our second example is find the derivative of s equals 5, and this is log, okay, of base 4 cubed of 2x plus 1. Okay, so I'm going to do them using the ln option, not the log one. Again, you've heard me throughout this lecture say that I prefer that method, so I'm going to do the remainder of these questions that way. So in this question, all right, the first thing to do is to kind of simplify this a little bit. And the way I'm going to do that is I'm going to rewrite the log in an easier form to take the derivative. So s is equal to 5 times the log of base 4 of 2x plus 1. And that whole log function is cubed. Okay, so that's an easier way for you to consider writing this. All right. I'm going to rewrite this 5 so it's a little easier to see. So now you can remember we're going to use the chain rule for this. Okay, so that means we have to let everything in the brackets here be equal to u. So u is equal to the log base 4 of 2x plus 1. So if we substitute that in, we get s equals 5u cubed. So remember, we can use the chain rule for this. And so ds by dx, again, because it's a function of x, is equal to 5 times the derivative of the function s with respect to u times the derivative of the function u with respect to x. Okay? So if we continue this, ds by du, okay, so we have ds by dx is equal to 5 times 3u squared, okay, taking that derivative, times du by dx. Okay, so to find du by dx, remember, it's 1 divided by u, or in this case I can call it v, times 1 over the ln of the base here, which is 4, times, we'll say dv by dx. So I used v instead of u here, just because we used u here. So v, again, is whatever is in the brackets of the log function. So we let v equal 2x plus 1. So our derivative, okay, du by dx, is equal to 1 divided by 2x plus 1 times 1 over the ln of 4 times dv by dx. Okay, so if you look here, dv by dx would simply be 2. Okay, because the derivative of 2x plus 1 is just 2. So if we substitute that value in, multiplied by 2. Now collecting these terms together, du by dx is simply equal to 2 divided by ln 4 times 2x plus 1. Okay, so I simply multiplied all the numerators together and then divided by multiplying all the denominators together. So we can now substitute all these items in. So ds by dx is equal to 15 times u squared. So u is the log base 4 of 2x plus 1 squared times du by dx, okay, which is 2 divided by the ln of 4 times 2x plus 1. Okay, so again, we can collect all of these terms together. So multiplying all the numerators together, we have 15 times 2 is 30 times the log of base 4, 2x plus 1, and that's squared, divided by the denominator. In this instance, there's only one term. So it's ln 4 times 2x plus 1. Okay? So again, what you're noticing here, the derivatives of the log and ln functions are actually relatively straightforward in calculating them. Okay? And then it's the exact same method that we've been using to do our other functions, okay, our inverse trigonometric functions, where we use, and trigonometric functions, where we use the chain rule. Okay? So the next item I want to talk about, and we've already touched upon this topic a little bit when we talked about derivative of log functions, is I want to talk about the natural logarithm. Okay? So the natural logarithm is actually the log of a function and the base is e. Okay? So that's the same as when you see the notation ln. Okay? So remember e, Euler's number, it's an irrational number that does not have a definitive end. Okay, so the decimals go on forever. And again, we call this the natural logarithm. So like I said, in this case, what we start with is the function y equals e to the exponent x. Okay, so our next section in this lecture will talk about the derivative of the e functions. But if we're looking at this purely from ln, then if you were to write this, you would have x, or in other words, the exponent is equal to the log of base e of the number y. Okay? In other words, like I've mentioned already, that's the same as the notation of ln. Okay? So that's the only difference between these. The other difference is if you have the ln of a function, the derivative is actually a little bit more straightforward. So if you have ln of a function u, the derivative is simply 1 divided by u times du by dx. Okay, so notice we don't have that 1 over ln of the base or the log of e to whatever the base is. Okay, so if we're using ln, the reason for that is the base is always e. So if you try to take the ln of the number e or the log of the number e, the base e, both these are actually equal to 1. Okay, so that's why you don't see that piece in the middle of this derivative here. Okay, so this derivative is actually the most straightforward, or one of the most straightforward. You'll see the derivative of the e function, e to the x, after we do a few examples. So our first example for natural logarithm is find the derivative of y equals the ln of 3x squared plus 2x. So again, the function in here is not just x, right? So it's some function. We'll let it be u. So u is 3x squared plus 2x. So in this case, substituting that, we have the y equals the ln of u, okay, in the exact same form that we just saw it in the previous slide. So dy by dx is equal to 1 over u times du by dx. So we have u. Du by dx is simply 6x plus 2, okay? Taking the derivative of those two functions here. So now substituting these in, dy by dx is equal to 1 divided by u, so 1 divided by 3x squared plus 2x, times du by dx, which is 6x plus 2. So combining these into one fraction, dy by dx is simply 6x plus 2 divided by 3x squared plus 2x. Okay, so you can see in this example how fast you can find that derivative. Okay, and it doesn't turn out to be, in this base case, that messy of a final answer. You'll see when you start compounding and doing a little more complicated versions of these derivatives, which we'll do in the next two examples. While the derivative piece is easy, once you substitute everything into these equations, it starts to get a little bit more complicated. Okay. So our second example is find the derivative of y equals 4x squared ln of 3x. So you can see here that we have two functions multiplied together. So that means we have to use the product rule. So to do that, we have to let one function be u, so we'll call the first function 4x squared, and one function be v, which is the ln of 3x. So the product rule, once you've set that, dy by dx is equal to the function u times the derivative dv by dx plus the function v times the derivative of u with respect to x. So the two terms we need are dv by dx and du by dx. Okay, so again, I like to place them on the side and do them there and then substitute them in. So du by dx is simple. It's simply going to be 8x. And dv by dx is equal to 1 divided by, remember, the function that's in the ln. So 1 divided by 3x times the derivative of that function 3x, which is simply 3. So if you do that, you'll notice these 3's will cancel, one in the numerator and one in the denominator. So this derivative is simply 1 divided by x. So now we have all four terms. We can simply substitute them into our derivative here. So dy by dx is equal to u, which is 4x squared, times dv by dx, 1 divided by x, plus v, which is the ln of 3x, times du by dx, which is 8x. Okay? So before just one item to simplify before we start collecting terms is you have an x squared here, and you have an x here. So this x will cancel, and this will just become x to the 1. Okay? So if I do that, dy by dx is equal to, in this case, 4x plus 8x times the ln of 3x. Okay? Now, if you're going to get fancy, I like to have it in kind of the most basic answer. You can see that you can actually factor these two numbers by removing a 4x from both. So if you do that, dy by dx is equal to 4x, and factoring that out, you get 1 plus 2 ln of 3x. Okay? If you need a refresher on factoring, what that means is if you were to multiply this back in, okay, you would actually arrive at the same solution that you have right here. Okay? So either one of those solutions I would mark as acceptable. Okay? You'll notice in my solution down here, I wrote it in the factored version. Again, if you're not going to factor it, that's okay. All right? Both of those I would accept as final answers. So our final example for ln, before we move to the e to the x function, is find the derivative of y equals the ln of 3x plus 2 divided by 4x. So in this case, unlike the previous example, there's two functions, but they're divided by one another. Okay, so in this case, you have to use the quotient rule. So following the same steps, you have to let u equal one function. Usually it's the one in the numerator, so ln of 3x plus 2. And v equal to 4x. So the quotient rule means that dy by dx is equal to the function v times du by dx minus the function u times dv by dx divided by the function v squared. So the items we need now are du by dx and dv by dx. So starting with du by dx, okay, that's equal to 1 divided by the function in the brackets of the ln, so 3x plus 2, times that derivative. So the derivative of 3x plus 2 is simply 3. So if you simplify that, you get 3 divided by 3x plus 2. dv by dx is simply the derivative. Make this look a little nicer. The derivative of 4x, which is simply 4. So now, just like we've done, now that we have all four of those terms, we can substitute them into the equation. So dy by dx is equal to v, which is 4x, times du by dx, which is 3 divided by 3x plus 2, minus the function u, ln of 3x plus 2, times dv by dx, which is simply 4. And that's all divided by the function v squared. So 4x all squared. So multiplying these out, we get dy by dx is equal to, the first term has 4x times 3, which is 12x divided by 3x plus 2. And the second one is simply minus 4 times the ln of 3x plus 2. There was no simplifying on that one. And that's divided by, if you multiply out 4x squared, you'll get 16x squared. Okay, so the final solution, has a lot of pieces in it. Okay, but the individual steps, again, even using the quotient rule, were relatively straightforward. Okay, taking these derivatives. Okay, our final section of this lesson is the exponential function. Okay, so what this is looking at is the derivative of an exponential function. Let's say, for example, 10 to the exponent 2x, or 2 to the exponent 4x squared plus 3. So basically you have a number, and it's raised to the exponent, and the exponent in this case is a function. Okay, so we can write that as y equals some number b to the exponent u. Okay, so throughout we've used u, right, as the symbol for whatever function we're talking about. So if we're doing the derivative of this, again, you're noticing that these are following kind of similar themes. So the derivative of this function, we'll call it b to the u, is equal to that same function, b to the exponent u, multiplied by the ln of whatever the base is, b, times the derivative of that function. Okay, so using this as using y equals 10 to the 2x. Okay, so I'm just taking the example from here. The derivative of that, dy by dx, would simply be that same function, 10 to the 2x, times the ln of the base, which is 10, times the derivative of this function. Okay, so the derivative of 2x is simply 2. So if you simplified this, you get 20 times, sorry, not 20, you get 2 times the ln of 10 times 10 to the 2x. Okay, I like simplifying with the numbers first, so that's, you can see why I took, that's why I took the 2 and the ln 10 and moved them before the 10 to the 2x. You don't have to do that, it's just my preference. So that's for a generalized function, doesn't matter what number it is. Going back to all of our talk about the number e, okay, that irrational number, if the base was e, okay, the derivative is a little bit simpler. So if it's e to some function, it's actually equal to e to that same function u times the derivative of that function. So there's no ln piece here. Okay, and again, that's because if you added that, and it was the ln of the number e, the ln of e is simply 1. Okay, so that's why it's not included in here. Interestingly, for this, let's say you just have e to the x. Okay, so the basic function, the derivative of e to the x with respect to x is simply e to the x, right? Because the derivative of x is 1. So it's one of those interesting functions where the derivative is actually the same as the function you start with. Okay, so that's kind of one of the quirks associated with e to the x. Okay, one of the reasons I show you it. But doing the derivatives for both these types is essentially the same. So this is the first of 2 examples I'm going to show you using the exponential function derivative. The first one is find the derivative of y equals 10x squared times 2 to the exponent x. Okay, you'll see here we have 2 functions. We have 10x squared and 2 to the exponent x. So I'm going to let u equal 10x squared and v equal 2 to the x. And since they're multiplied together, we can use the product rule. So dy by dx is equal to u times dv by dx plus v times du by dx. Okay, so the last two pieces we need are those two derivatives. So starting with du by dx. Okay, so the derivative of 10x squared is simply going to be 20x. And for dv by dx, again, following that derivative function, remember it's 2 to the x, so it's the same function, multiplied by the ln of the base, so the base here is 2, times the derivative of the function that's sitting in this exponent. In that case, the derivative of x is simply 1. So dv by dx is 2 to the x, ln 2, I always like the numbers first, ln 2 times 2 to the exponent x. Okay? Having all these functions now, we can simply substitute them in. So dy by dx is equal to u, which is 10x squared, times dv by dx, which is ln 2 times 2 to the x, plus v, which is 2 to the x, times du by dx, which is 20x. Okay, so I'm going to do some factoring here. I'll do it in steps. There's two items that jump out at me that I can factor. Okay, the first is that both of these numbers have a 2 to the exponent x. So we can start by factoring that component out. So dy by dx is equal to 2 to the exponent x. Okay, that's factored out. So we remove it from both of those expressions. So we're left with 10x squared ln 2 plus 20x. The next item that jumps out at me, okay, is we have a 10x squared here, and we have, I'll do it in a different color. We have a 10x squared here and a 20x, okay? So we have one x that we can factor out, and we can actually factor out 10, right? Because 10 works in the first, and in the second one, 20 can factor to 10 times 2. So factoring out a 10x, we get dy by dx is equal to 2 to the exponent x, and that's now x ln 2, sorry, I forgot to factor out the 10x we just talked about. So 2 to the exponent x times 10x, and then in brackets, we can remove 10x from both of these expressions. So we're left with just x ln 2 plus, and if we remove 10x from the second one, we're left with just 2. Okay, so that's about as far as we can go factoring. Okay, again, you don't have to factor it to that extent. I think the final solution looks a little bit cleaner when it's factored this way. Again, that's totally up to you. I do encourage you to try and get used to factoring because it does help you start to be able to pull out common terms, okay, when you're looking at multiple expressions. So our last example for this lesson, okay, is find the derivative of r equals 10 to the exponent 2 theta and e to the exponent theta. So we don't have a typical dy by dx here, but what you will notice is we have two functions, both of them are functions of the term theta. So again, we're going to use the product rule here. And if we do that, we'll let u equal 10 to the exponent 2 theta and v equal e to the exponent theta. Okay? So if we're using the product rule for this, we have dr by d theta, since the function is a function of theta. That's equal to u times dv by dx plus v times du by dx. So our last two terms that we need, okay, are those derivatives. So we'll start with the first one, du by, sorry, I wrote x here. There's actually should have said dv by d theta. So you can see that even I get used to having it as something by with respect to x. Okay, so make sure you have the proper notation. So the first one, du by d theta, not x, is equal to, again, because this is a number, okay, to the exponent with a function. It's simply that same function, 10 to the 2 theta, times the ln of the base, which is 10, times the derivative of the function in the exponent. So the derivative of 2 theta, okay, is simply 2. Now, if you look at dv by d theta, okay, remember for the function e, it's simply that same function, e to the theta, times the derivative of that function, okay, so it's just theta, so the derivative is simply 1. So this is simply e to the exponent theta, okay? Again, one of those quirky items when you're dealing with a function, that's e. So if you substitute all of these values in again, dr by d theta is equal to u, so 10 to the 2 theta, times dv by d theta, which is e to the exponent theta, plus v, which is e to the theta, times du by d theta, which is 10 to the 2 theta, ln 10 times 2. So you're going to notice, again, I'm going to factor this, and you can see two common terms in here. You can see that both of them have 10 to the 2 theta, and both of them have e to the theta. So we can factor both those out. So we have dr by d theta is equal to 10 to the 2 theta times e to the theta. So we took everything out of the first term, so all that's left would be 1. Plus, we removed the e to the theta and the 10 to the 2 theta, so we're just left with 2 times ln of 10. Okay? Now, you actually could simplify that to a number. I like to just leave it as 1 plus 2 ln 10. Okay? Again, totally up to you, and totally up to you if you want to factor. All right? But I do encourage it. So that's it for this lesson. We have one more lesson left in this unit, and that's when we're going to look at what's called L'Hopital's rule. In the meantime, I have exercises from two sections, 27.5 and 27.6. I encourage you to try all these questions. All right, bring questions you might have to a tutorial session. And I wouldn't try to do other questions within the exercises unless you want another challenge. Some of them you may not be able to do because they rely, as I've said in the past, on information in chapters we may not have covered in this textbook. Okay, so any questions, just send me an email. Thanks, everybody.